Okay, so hi. So for this video, we will be discussing another property of Laplace transform, which is the division by t. Okay, so theorem. So if the Laplace transform of f of t is equal to f of s, then the Laplace transform of f of t divided by t is equal to the integral of f of u du from s to infinity, provided that the limit of f of t divided by t at t approaches to 0 exists. Okay, so this can only be applied if the limit exists. Okay, so the first thing that you should do if you can see a problem, a Laplace transform problem that is division by t, is to test if the limit exists. Okay, so if the limit exists, so then what you need to do is find the Laplace transform of the numerator. Okay, so the Laplace transform of the numerator f of t is equal to f of s. So to get the Laplace transform of f of t over t, then you will replace the s, okay, in the Laplace transform of the numerator. So you will replace it with u and then integrate it with respect to du from s to infinity. Okay, so example, so find the Laplace transform of f of t is equal to sine of t over t. So again, first is to check if the limit exists. So the limit of sine of t over t, okay, at t approaches to 0, so is equal to, so this is a theorem from differential calculus, limits, so its value is 1. Okay, so therefore the limit exists. So therefore we can apply this theorem here. Okay, so next is find the Laplace transform of the numerator. So our numerator is sine of t. So we need the Laplace transform of sine of t. Okay, so from the formula that we have already memorized, so the Laplace transform of sine omega t is equal to omega over s squared plus omega squared. So here our omega is equal to 1. So therefore we will have 1 over s squared plus 1 squared. So that is 1. Okay, so this is now our f of s. Okay, so since we need to find f of u, okay, so all we need to do is replace s with u. Okay, so our f of u is equal to 1 over u squared plus 1. Okay, so now we can now solve for the Laplace transform of sine t over t. So the Laplace transform of sine of t over t is equal to the integral of f of u du. So our f of u is 1 over u squared plus 1. So 1 over u squared plus 1 and then du. Okay, from s to infinity. Okay, so as you can see, we have infinite limit, so therefore this is an improper integral. So therefore we must replace infinity with another variable. So let's say a, and then write the notation of limits. So we can rewrite this instead as the limit of du over u squared plus 1 from s to a as a approaches to 0. Oh, sorry, a approaches to infinity. Okay, so integrating this, so this is inverse trigonometric function, arctangent. So we will have the limit of our a is 1, so 1 over a arctan of u over a, okay, from s to a as a approaches to infinity. Okay, so we can now substitute the limits. So this will become arctan of u, so substituting a to u, so we'll have arctan of a minus arctan of s. Okay, and then we'll have a approaches to infinity. Okay, so if we substitute infinity here, we'll have arctan of infinity, then our value is, we can have a lot of values. So arctangent of infinity could be pi over 2, 3 pi over 2, and so on. So our value is equal to pi n over 2. Okay, so but we cannot use that here, so therefore we must look for a way so that we can evaluate this. Okay, so what we can do is we can combine this. Okay, so if we let z, say for example, as arctan of a minus arctan of s, oops, okay, and if we also let arctan of a as x and arctan of s as y, therefore we will have z is equal to x minus y. Okay, so if we get the tangent of both sides, so we'll have tangent of z is equal to tangent of x minus y, right? So using the identities of tangent, so tangent x plus y, so that is equal to tangent of x minus tangent of y over 1 plus tangent x and then tangent y. Okay, so that is tangent of z. So therefore, getting the arctan of both sides, so z is equal to arctangent of tangent x minus tangent y over 1 plus tangent x tangent y. Okay, but since we let x as arctan of a, so since a is equal to, since x is equal to arctan of a, okay, so then tangent of x is equal to a, and since y is equal to arctan of s, okay, so therefore tangent of y is equal to s. So we can replace arctan of x with a, and we can replace tangent of x with a and tangent of y with s. So therefore z is equal to arctan of, we have a minus s over 1 plus as. Okay, so since we let arctan of a minus arctan of s as z, therefore arctan of a minus arctan of s is also equal to arctan of a minus s over 1 plus as. So therefore, rewriting again, the Laplace transform of sine of t over t is equal to the limit of arctan of a minus s over 1 plus as a approaches to infinity. Okay, so again, if we substitute infinity to a, so this will become still indeterminate, okay, because we will have infinity over infinity. So therefore, what we can do is we can divide all the terms with the highest degree that a appears. So in this case, a only appear at the first degree, so we can divide all the terms with a. So the limit of arctan of, divide everything by a, so this will become a over a minus s over a over 1 over a plus as over a. Okay, as a approaches to infinity, simplifying, this will become the limit of arctan of a over a is 1 minus s over a over 1 over a plus, canceling out a, so we'll have plus s as a approaches to infinity. Okay, so as you can see, these terms now, s over a as a approaches to as a approaches to infinity will become 0, and 1 over a as a approaches to infinity also becomes 0. So therefore, the Laplace transform of sine of t over t is equal to arctangent of 1 over s. Okay, so this division property is very tricky, okay, because it has an infinite limit. So therefore, we must make sure that when we substitute the limit approaching infinity, we should make sure that it will not be indeterminate. Okay, so based on the things that we have learned in differential calculus about indeterminate, what we call this, indeterminate limits, then we have to use our knowledge, okay, of those indeterminate limits so that we can evaluate the limits properly. Okay, so one thing is we can, like what we did here, we did not substitute infinity directly, okay, but we rearrange this. Okay, we rearrange this into a form where the resulting term, okay, is not indeterminate. Okay, so I guess that's it. Okay, so another example. So find the Laplace transform of the function f of t is equal to e raised to negative at minus e raised to the power of negative bt over t. Okay, so let's check if the limit exists. Okay, so we have the limit of e raised to negative at minus e raised to negative bt over t as t approaches to 0. Okay, so we can use the L'Hopital's rule in here. Okay, so we can derive the numerator and then derive the denominator to see if the limit exists. So limit, so this will become negative a e raised to the negative negative at plus b e raised to the negative bt over 1 as t approaches to 0. So this will become negative a plus b. Okay, so limit exists. Okay, so since the limit exists, then we can apply the property of division by p. Okay, so the Laplace transform therefore of e raised to the negative at minus e raised to the negative bt over t is equal to, we can find first the Laplace transform of this, the numerator. Okay, so erase. So Laplace transform first of the numerator, e raised to negative at minus e raised to the power of negative bt. So that is equal to the Laplace transform of e raised to the negative at minus Laplace transform of e raised to the power of negative bt. So we will have here 1 over s minus negative a minus, so minus minus 1 over s minus negative b. Okay, so this is 1 over s plus a minus 1 over s plus b. Okay, so this is our f of s. Okay, so therefore our f of u is equal to 1 over u plus a minus 1 over u plus b. Okay, so therefore, so rewriting this, so therefore the Laplace transform of e raised to the negative at minus e raised to the negative bt all over t is equal to the integral of f of u, which is this, so 1 over u plus a minus 1 over u plus b du from s to infinity. Okay, so again we can replace infinity with another letter, so since we already have a, b, so we can use c. So the limit of the integral of 1 over u plus a minus 1 over u plus b du from s to c at c approaches to infinity. Okay, so this is simple integration, so I think we can integrate this using natural logarithm. So the limit of, we will have here ln of u plus a minus ln of u plus b, okay, from s to c, okay, as c approaches to infinity. So using the properties of logarithm, we can combine this. So the limit of ln of, we will have u plus a over u plus b, okay, from s to c as c approaches to infinity. So we can now substitute the limits. So we will have limit of, this will become ln of c plus a over c plus b, okay, minus ln of s plus a over s plus b. Okay, so as c approaches to infinity. Okay, so if we substitute infinity immediately, so this will become infinity over infinity, and then ln of infinity is infinity. So therefore we cannot substitute that directly, so we can use the technique that we have used in this previous example. So we will divide all the terms in this term, we will divide all the terms, okay, with c, okay, the highest degree that c appears. Okay, so this will become okay, so we still have space here, so the limit of ln of c over c plus a over c over c over c plus b over c. Okay, and then just rewrite the second term, so ln of s plus a over s plus b. Okay, so as c approaches to infinity. Okay, so this will become the limit of ln of, the numerator will become 1 plus a over c over 1 plus b over c minus ln of s plus a over s plus b. Okay, so as c approaches to infinity. So as c approaches to infinity, so this will become a over c. As c approaches to infinity, that will become 0. b over c, as c approaches to infinity, also becomes 0. So what will remain is ln of 1. Okay, but we know that ln of 1 is equal to 0. So therefore, what will remain is this. Okay, so it's equal to negative ln of s plus a over s plus b. Okay, so this is now the Laplace transform. Or you can also express it if you don't want to have a negative sign, then you can transfer the negative sign in the exponent. So s plus a over s plus b raised to negative 1. So that means it's the reciprocal. So we'll have ln of s plus b over s plus a. Okay, so that is now the Laplace transform of e raised to negative at minus e raised to the negative bt over t. Okay, so again, the knowledge of limits, okay, so in this property is very essential. Okay, so you should not substitute directly, okay, the infinity. So you should always find a way so that like this, okay, so like this you will avoid having terms that are indeterminate, okay, or has values of infinity, because in Laplace transforms, so your Laplace transforms should only involve s. Okay, so that's all. So I hope that you have understood this lesson, and also you have reviewed your theorems in limits. Okay, so that's all, and good luck.